Using a single vertical or horizontal line, split the samples into the two classes. Potentially, this is the type of solution that you came up with. Now, using a further vertical or horizontal line to either the left or the right of the existing vertical line, further split the samples into the two classes. Again, potentially this is the type of solution that you came up with. Now, think, what was the rationale behind your answers? This is how decision trees algorithms work. These are algorithms that iteratively split data one feature at a time. Every split produces two groups, what we call the left and the right-hand side of the split. And the process is as follows. So first, for each feature, we explore what is the best value that we want to use as a threshold to create a split. So that values lower than that threshold correspond to one class, and values greater than the threshold correspond to the other class. Then we, based on the findings of this step, we compare the splits across all the features and decide which of the features we want to use for the split. So which of those splits is the most convenient to us. And then finally, we decide whether we want to go ahead with the split or not based on certain criteria, which we will talk about later. Decision trees try to maximize a concept called, try to minimize the concept of impurity. In a sense, a node is said to be pure if all the samples belong to the same class, whereas there is a perfect mix between two classes, for example, so that 50% of the samples belong to one class and the other 50 to the other class, then we say the sample is maximally impure. There are different ways of defining impurity. Typical ones, a very common one is to use the Gini index. So the Gini index will range between 0 for pure nodes to 1 for maximally impure nodes. And we start by defining the Gini value for a given node, and then where P sub C is just the proportion of samples in the node that correspond to class C. And then what we do is we take the two nodes, the left node and the right node. Remember that this is the splits produce a left node and a right node. So what we do is we compute a weighted average of the Gini values for each of those nodes, the left and the right node, weighted by the proportion of parent samples falling within each node. Impurity is also commonly defined using the entropy. And in this case, a pure node has a value of 0 and a maximal impure node has a value of 0.5. So how does this work? Well, we start with the data at the top, and then we scan all the data and produce the first split. And this is what we call the root node, the node at the top, the very first node of the decision tree. Then we investigate the left split and see whether we want to further split this node. Potentially we do. And then we move to the resulting left node and we investigate whether we further want to split this, and potentially we see that we want. And then let's say that the nodes that we get, both of the nodes we get, are in this case nodes that we don't want to further split, as you know, and we decide this after we explore them, again based on some criteria which we will see soon. And these nodes then are called leaf nodes because they are nodes that are not going to be further split. So we have the root node, we have leaf nodes, and nodes that sit between the root node and the leaf nodes are called decision nodes. So then we go back up and we explore now the right hand side of the split. And let's say that now, for example, the split, after investigation, we decide that we don't want to further split this node, and therefore now it's a leaf node. And then we keep going back up and checking the right hand side, and we continue this process until we don't want to grow the tree anymore. There could be different reasons why we decide not to keep growing the tree, not to keep splitting nodes. For example, if a node is pure, it doesn't make any sense to keep splitting it because it already contains only samples from one class. It could be also that we reach a predefined maximum depth of the tree, which is the maximum number of consecutive splits that we want to apply on the data. Also, it could be that we end up with nodes that have too few samples. We don't like nodes with too few samples. In the same way, we don't like running a statistical analysis on very small samples sets. And that is because, well, if a node only has one or two samples, is that really representative of anything? We don't know. It could very well be an outlier, in which case the tree will be overfitting the data. Now, okay, let's now think about the different variables that come into play into decision trees. What are the hyperparameters and what are the parameters of decision trees? Well, hyperparameters will be, okay, what type of impurity metric are we going to use? We talk about them, we mentioned two earlier. What is the maximum depth of the tree? So how many consecutive splits do we want to apply on the data? And then what are the minimum number of samples that we want to have in a node to even consider splitting it? And also what are the minimum number of samples that we want, or what is the minimum number of samples that we want to have in a node in order to consider the node a leaf. And again, all these parameters, or sorry, the last three parameters, the maximum depth and the minimum number of samples for a split and the minimum number of samples in a leaf, they are all geared towards avoiding the tree to overfit during training. So then, okay, all of these variables need to be set beforehand. We can't decide, there is no way for us to decide what is the optimal value of these by just looking at the training data. So then what are the parameters that the decision tree needs to learn, and it can indeed learn them automatically by consuming training data? Well, the splits. So all the root nodes and all the different decision nodes. So all the different thresholds for each feature applied in each of these nodes to generate the splits. Those are the parameters. There are many different types of decision trees, ID3, C4.5, CART, and these can also be combined in different ways. We have the boosted trees or the bootstrap aggregated or ensembled trees, which this is where random forest will fall within. I'm also there giving you the title of a paper that goes through a number of decision trees for you to scan. What are the advantages and disadvantages of decision trees? Well, in terms of advantages, it's very intuitive and a very straightforward concept, as we have seen. It produces models that are very easy to interpret because we just need to follow the tree and look at the different very simple splits based on a single threshold, based on a threshold applied to a single feature each time on each step. And it can handle mixed data with continuous and categorical variables. In terms of these disadvantages, it can be unstable. Decision trees can very easily overfit the training data, which is why we need all those, we need to carefully set all the hyperparameters that we discussed earlier. They can be expensive to train because they need to scan the data several times. And also, if the trees that we want to build are very complex and large, this can take quite a bit of time. And then the output of a decision tree is not smooth at all. It's based on vertical and horizontal lines stacked together or grouped together. And therefore, it's going to be full of angles. It's not going to be smooth.